In today's lecture, we start with the topic of machine learning. We will have 7 lectures in this series. Today, we will give an introduction to this topic. The instructional objectives of today's lectures are the following. We will first look at what we mean by machine learning. We will look at several definitions of the term machine learning. In this class, the student will be introduced to some different learning frameworks, and then we will introduce some of the basic notations. Also, the student will be made familiar with certain example applications of machine learning. Specifically, we will give an introduction to the type of learning which we call concept learning. In this context, the student will look at certain things, what are the concept of features that are used in a learning problem. We will look at what we mean by a hypothesis space or a set of hypotheses, and what we mean by a hypothesis that we are trying to learn. We will introduce what we mean by a training set and a test set. We will also talk about the instance space. Also, we will very briefly introduce the notion of inductive bias. On studying this lesson, the student should be able to formulate a given concept learning problem. Given a problem, they should be able to identify the possible features that may be relevant to the problem, and they should be able to get an idea of the hypothesis space that they need to consider. In subsequent lectures, we will look at different algorithms and different types of representation issues. So, with this we start today's lecture. First of all, the definition of learning. Learning covers a broad range of processes. Learning covers a broad range of processes. It means to gain knowledge or an understanding of a skill in something. So, when we say that we want to learn, we want to gain knowledge about or understanding about or expertise in solving some problems, and this expertise or this knowledge can come by looking at examples or by gaining experience. By examples experience, or this knowledge can come by studying the problem domain or by being told, that is by instruction. There are several parallels between the process of human learning and artificial or machine learning. Some techniques in machine learning derive from the effort of psychologists to derive theories of human or animal learning through computational model. The field of cognitive psychology has dealt with in trying to understand how humans learn, and in some cases they have also tried to identify certain computational models to model the way humans think and the way humans learn. In machine learning, on the other hand, has dealt with different techniques, some of which are inspired by human learning techniques as derived from cognitive psychology, others by different symbolic techniques which are efficient to do by machines. but it is conceivable that the concepts and techniques being explored by researchers in machine learning may actually help understand certain biological processes. So, there is a lot of cross fertilization between the fields of cognitive psychology, which tries to understand human or animal learning, and the field of machine learning, where objective is to solely learn by help of machines. Now, before we formally define learning, let us look at a few of the definitions that people have put forward on machine learning. The first definition that we will take up is the definition by Donald Michie in 1991. This definition states that a learning system uses sample data to generate an updated basis for improved performance on subsequent data from the same source and expresses the new basis in intelligible symbolic form. So, let us try to understand what this means. So, we have a learning system which uses sample data, that is the training example, which we call a training example. So, there is some sample data or there is some experience to go by, and on the basis of this experience, the system tries to generate a new thing, a new model, so that it can lead to improved performance on subsequent examples. So, the system uses input data to get a model which can help it to improve its performance on new data, but data that is coming from similar sort of examples, data from the same source. And this model or this thing that has been learned is expressed in a symbolic form which can be understood and which can be manipulated. So, this is the definition by Donald Michie. Let us look at the definition by another pioneer in the field, Herbert Simon. This definition says that learning denotes changes in the system that are adaptive, in the sense that they enable the system to do the same task or tasks drawn from the same population more effectively the next time. This is a similar definition, as you can see. So, this definition says that learning means there is some change in the system, and this change enables the system to perform better on similar tasks in future more effectively. Okay. So, we see that there are several other definitions by different other practitioners in the field, but we see that this type of learning mainly talks about there being some input data or experience from which the system learns, and the system tries to improve its performance, and this improvement in performance must be measurable in some way. So, there must be performance measure which must be improved due to learning. So, by learning from examples, the system is able to improve its performance. Secondly, some of these definitions also emphasize the comprehensibility, that the new thing that the system has learned must be expressed in a form that will be understood. So, a well posed, so let us now try to define simply a well posed learning problem. A computer program is set to learn a task T. So, T is the task that the system is trying to learn. And what is the basis by which the system is learning this task T? The system is given some data which is the experience E, and the system is learning to improve its performance in task T with respect to a performance metric P. That is, the system's performance in the task T improves with experience E as measured by the performance metric P. So, this is the definition of learning which we will accept, and on this basis we will carry on our further studies. And to put it in a more natural form, learning is the improvement of performance in some environment through the acquisition of knowledge resulting from experience in that environment. So, to understand this definition, let us go back to the framework of an intelligent agent, which we have been looking at in this course. So, if you remember, we have this structure, we have this agent and we have this environment. The agent takes action which changes the environment, and the agent can sense the environment. So, this is the environment. The agent gets experience, a set of sensory output, etc. So, agent gets experience by interacting with the environment, and this results in acquisition of some knowledge, and using this knowledge the agent can actually improve its performance in certain tasks. So, this is the formal definition of learning. Now, let us look at a few examples of learning problems to make this more concrete. So, let us say that we want to know whether a particular given patient has a possibility of having let us say brain tumor. And what is the experience? We have the database of previous patients, the ones who have been diagnosed with tumor and ones who have been certified as having no tumor, and we have access to the patient records, which include different data about the patient as well as, let us say, some images like MRI images or something. So, we have some data about past patients having tumor, and we wish to find out, given a new patient and his records, we want to know whether this patient is likely to have tumor. The second example, let us say that our task is to recognize speech. So, the machine should be able to hear, let us say, me speak, and it should be able to recognize the speech and take dictations. So, in this case, what can be used as experience is a database of speech which have been already recognized and their transcripts are available. So, we have speech and their transcripts that constitutes the experience, and as a result of this experience the system should be able to learn. And how do we measure whether the system is successful? We measure the percentage of correctly recognized words. Okay. So, the success in the learning task can be measured by the accuracy or the precision, that is number of words which have been, number of examples which have been correctly labeled or correctly recognized. Okay. And the error can be measured by looking at the number of misclassifications, number of words which have been wrongly recognized. Okay. So, we want to recognize all correct cases. For tumor, for let us say tumor, we want to recognize, label as positive all those patients who really have tumor and none of the patients who do not have tumor. So, we can measure it by accuracy, or we can measure it by two terms which we will talk about later, precision and coverage. So, precision accuracy is the number of examples that we label as having tumor, and we want to know what percentage of them actually have tumor, and coverage means that out of the patients who actually have tumor, how many of them do we correctly recognize as having tumor. So, these are the different measures that we use for measuring the accuracy or the correctness of a learning task. So, the learner is in an environment, and the learner is attempting to learn something about the environment so that it can perform some of its tasks well. The learner is linked to some knowledge base from which it can draw and which stores acquired knowledge. The learner has a knowledge base. There could be some prior knowledge in the knowledge base, but as a result of learning, the learner is able to update its knowledge base. And this knowledge is usually stored in some form of internal data structure. You have studied logic and you have seen representation languages in logic, in first order logic. You have also looked at possibly certain other representation schemes as frames, etc. So, knowledge is basically stored in one of these representation schemes. And what is the experience? The experience is basically derived from the perceptual input of the agent, and the agent can take some actions, which is the motor output of the agent. And the performance of the agent is measured by some quantitative performance is measured quantitatively by several aspects, which depending on the task we decide what we use. Now, before we let us just review why study of machine learning is so important. There are many tasks that require an adaptive system, that require a system which can learn. For example, handwriting recognition, speech recognition, these are examples where an adaptive system is required. Learning is also useful as an alternative to hard coding a program. For example, suppose you want to develop a program which can play the game of chess. Now, you could write a program in which for every different possible situations you can specify what move the agent should take. So, you could hand code all the rules that are useful for playing chess. An alternative way of writing such a program would be to provide the system with a database of chess games and their outcomes, and maybe the system can apply learning to learn to play a good game of chess without you explicitly having to tell the system which move to take in which situation, but you give a large database of games by which the system can figure out. Providing a database of games is usually easier than hand coding the rules. So, you can save a lot of manual effort if a system is able to learn. Also, the study of machine learning, as we discussed earlier, also gives us an insight into human learning, and we try to study, for example, learning of language is a very non-trivial task. So, trying to understand how we can make a machine learn a language can give us a clue as to how humans acquire language. And machine learning has been very useful in the carp of data mining, which helps systems to acquire hidden rules from data. So, which has opened a whole new area of applications. So, this is a new kind of capability that our systems are provided with. There are many types of learning, and learning we can classify learning along different dimensions. Supervised learning, in supervised learning the system is given labeled training examples. These labeled training examples consist of, we have a set of examples and we also have their labels. So, we have the inputs and the outputs of the examples. And in unsupervised learning, is learning where there are no labels given. We only have the examples which are not pre-classified. So, we have unclassified training examples, and there are situations where we would like to learn from them. So, in this series of lectures, we will mainly be concerned with supervised machine learning, where we are given labeled examples. The concept learning we will talk about, we have a set of labeled examples during training, using which we will learn to classify an unknown example. There are also other types of learning where we do not have labeled examples, but we try to learn. A third type of learning is reinforcement learning, In reinforcement learning, we are not given just examples and each one of them is labeled, but we are given a sequence of examples, and at some points the system gets some reward or some punishment. These are called reinforcements. For example, when a system is playing a game of chess, the system does not get to know whether each move is good or bad. Each move is not rated, but at the end of the game the system knows whether it has won or drawn the game or lost. So, that is the reinforcement which is available at only certain points in the game. Okay. So, in reinforcement learning, the system is trying to learn, but it gets reinforcements only at certain times. Now, what are the types of knowledge that can be acquired by learning? The type of knowledge can be declarative knowledge, that is knowledge which can be expressed in terms of concepts, in terms of preferred value of parameters, or in terms of grammars, or in terms of taxonomies. The knowledge acquired by learning can alternatively be expressed as procedural knowledge. Procedural knowledge can be expressed in the terms of rules, rule strengths, graphs or networks, computer programs and plans. Certain data structures that can be used for storing learned knowledge are, we are just looking at talking about some of these. A few of these algorithms we will see later in this course. So, certain data structures are decision trees, logical expressions, neural networks, condition action rules, sets of rules, finite state automata and programs. For example, concepts, when we want to represent concepts, we can represent concepts by decision trees or by logical expressions or by neural networks. Behavioral rules can be expressed as condition action rules. Plans can be expressed as sets of rules or by finite state automata. Computer programs can be expressed as C code. And then there could be different strategies by which knowledge, these learning rules can be acquired. Inductive inference can be used to learn concepts or to learn grammars. Evolutionary learning or genetic algorithms can be used to learn certain preferred values of parameters. In unsupervised learning, clustering can be used for learning taxonomies. And then we can also have analogy or induction to learn rules. We can have reinforcement learnings to learn plans or strategies or what you call policies, evolutionary learning, stochastic learning, etc. So, there is a wide choice of learning strategies, learning programs, and a few of these we will be studying in this course. Now, how do we evaluate learner? Once we have a learning strategy, typically what we do is we draw a learning curve. In a learning curve, what we do is we plot the accuracy of the learner along the y axis. This axis is the accuracy, and along the x axis we plot number of training examples seen. So, what we typically expect is that the accuracy of the learner will increase as the number of training examples increases. So, these are typical learning curves that we might get. So, these learning curves plot the accuracy or precision in terms of the number of training examples seen. Now, next we will talk about inductive learning for classification, also known as concept learning. In fact, in most of the lectures on learning in this course, we will mainly be looking at the idea of concept learning. So, what is concept learning? Concept learning or classification means learning a description of a class of objects. So, we have some concept or some object whose description we wish to learn, and concept learning is learning this description. And why do we want to learn this description? We want to use this description to predict the class of a new object. When we have a new example, we want to know which class this new example belongs to. So, we try to learn the description of a class. So, we are given an animal, we want to know whether this animal can be classified as a tiger or not. And what we have is, we have seen in the past several animals which we are told are tigers, and we also have seen several animals which we are told are not tigers. And from this we will form a model of what is a tiger, and so that given a new animal, we will be able to know whether this animal is a tiger or not a tiger. So, this is the essence of concept learning. There are other examples of concept learning tasks, some of them are described here. Suppose our objective is to classify parts as defective parts or okay parts. Second example, mammogram analysis. We are given a mammogram and we want to classify the mammogram as normal or precancerous or cancerous. Example 3, in document understanding, we are given a rectangular region from a scanned image, and we want to be able to say whether this is a text region or graphics region. So, we want to recognize a text region from a graphics region. So, these are certain examples of a concept learning task. Now, we will be using inductive inference for concept learning, and let us first see what we mean by inductive inference. Now, suppose H is a hypothesis and F is a set of facts. Suppose we know that H implies F. If H implies F is valid, this rule H implies F is valid, and H is known to be true, then by modus ponens, which you have studied, F must be true. H implies F is valid, the antecedent H is known to be true, then logically by modus ponens it follows that F must be true. This is an example of deduction, logical deduction. So, we can derive F from H. This process is truth preserving, and this is called deductive inference. You are already familiar with deductive inference. Let us take an example. That suppose you know that you have seen, you know that all men are mortal, and you know that Socrates is a man, you can conclude that Socrates is mortal. So, this is an example of deductive inference. Now, let us see next what we mean by inductive inference. Suppose again let us assume that H is a hypothesis and F is a set of facts, and again let us say that H implies F is known to be valid. Now, suppose we know F. Now, knowing F, in inductive inference we will try to derive H. Now, from F, H does not follow by deductive inference, okay. But if F is false, then H must be false. If F is true, deductively we cannot say that H must be true, but if F is false, we can say that H must be false. So, deriving H from F is falsity preserving, but not truth preserving. So, if there are some facts which make F false, then H must also be false. But in inductive inference, we will derive H from F. Okay. So, suppose on 10 days I have woken up and seen that in the morning the sky is blue, and on the basis of this I form a hypothesis that in the morning the sky is always blue. So, this is an example of an inductive inference. On the basis of 10 data of the sky being blue in the morning, I am inferring that the sky is always blue. This is an example of inductive inference or induction. As an example of another example of induction, suppose you see 5 white tigers. You see 5 tigers and all of them are white, and you conclude all tigers are white. So, this is an example of inductive inference. When can you be wrong? Suppose now you find a yellow tiger. Now, this falsifies your conjecture. So, inductive inference is not a logical inference, so it does not preserve the truth, but it is a useful leap to take. It gives you new knowledge, knowledge that you have not already seen. An example of deduction which I already mentioned, suppose you are told that all men are mortal and you know that you are a man and you conclude that therefore you are mortal. So, this is an example of a deductive inference. What we saw earlier is an example of a inductive inference. Now, let us look at concept learning in more detail. Suppose you have a goal concept that you are trying to learn. So, we will call this goal concept a target concept. A target concept is the concept that you are trying to learn. For example, you are trying to learn what is a tiger. So, tiger is the target concept. And your guesses of the target concept is the hypothesis. So, you are trying to learn the concept and you make a hypothesis. You form a hypothesis about the description of the concept. So, a hypothesis is your guess or approximation of the target concept. And how do you form the hypothesis? By looking at data, by looking at many instances of data or examples. So, an object which is used to help you learn the goal concept is called an instance or an example. An instance or an example is something which helps you learn the goal concept. So, typically an instance is described by a vector of features also called attributes. We will see some examples of attributes. Suppose you are given a new animal and the attributes are color, number of legs, whether the animal has whiskers, length of the body, whether the animal has fur, and so on. So, these are the features. So, if you are given an animal whose color is white, it is furry, it has a tail, it is 6 feet long, it has whiskers. This is a description of an instance of an animal. So, an instance is described by a vector of features. Features are also called attributes. So, for example, an instance is given by x1, x2, xn. x1 is the value of the first feature, xn is the value of the nth feature. There are different types of feature that we can have. Features can be nominal. For example, color of the animal. Color can be red, yellow, blue, green. So, these are some specific values. They are not directly linked to each other. Okay. So, nominal is like color is a nominal attribute. Similarly, suppose you are trying to learn an object, whether an object is a table, and one of the attributes you can have is what material is the object made of, and the material can be wood, steel, glass, etc. So, these are nominal attributes. Secondly, you can have numeric attributes. Among numeric attributes also, the attribute can be, numeric attributes are usually ordered. Some other attributes are also ordered. Ordered means there is an ordering to the values. For example, length of the animal. This is a ordered attribute. It is 5 feet, 6 feet, 4 feet, 8 feet. So, they have some relationship with themselves. These are ordered attributes. Temperature, weight, length, these are examples of ordered attributes. Thirdly, attributes can be structured. If there is some structure in the order of the values, but they are not fully ordered. For example, if the values can be put into some sort of generalization hierarchy or some partial order. For example, if you consider the animal taxonomy, this is an example of the animal taxonomy. Suppose you have the class vertebrates. So, you know that animals can be classified into vertebrates or invertebrates. Among vertebrates, you can have mammals, reptiles, etc. Among mammals, or well, I do not know reptiles as a vertebrate, but yes, mammals, birds, fish. So, these are vertebrates. Among mammals, you can classify them as 4-legged mammals and 2-legged mammal. Under 4-legged mammal, you have tiger, mouse, deer, etc. Under 2-legged mammal, you have human, kangaroo, etc. So, this is an example of a classification hierarchy, and this is also an example of a structured attribute. And in this direction, we have more general classes. So, the concept learning problem formally can be described as follows. We are given a labeling function f. F is an underlying function for describing the concept. This function f maps feature vectors into some classes. So, we have a discrete set of k classes. There are k possible classes. For example, we have 2 classes, tiger or not tiger, or we can have 3 classes, whether it is a tiger or a lion or a deer. Okay. So, in general, we have a finite set of classes. So, we have k classes, and we have a actual underlying function that maps an input instance to one of these classes. So, the function f maps an input instance to one of these classes. So, this is given to us. In a special case, we may have only 2 classes. In that case, we will say that one of the classes is a positive, the other is negative. And we are given some training examples. Each training example is a pair, the instance and its classification. Oops. So, each training example is given as a pair, the instance and its class, and we have a set of such training examples. So, using these training examples, we want to learn an approximation of f. So, from the set of x f x pairs that we have got, we want to learn the target concept f. So, f is what we wish to learn. So, given a set of x f x pairs, we want to infer f, we want to inductively infer f. Now, if you are given a finite sample and you are not shown all the instances, it is not really possible to guess the correct value of f with absolute certainty. Okay. So, we will apply inductive inference and we will try to find some pattern in the training examples, and we will assume that this pattern will hold for future examples also. This is an example of training set. We have, this is an instance x equal to 1, then classification is 1, x equal to 2, f x is 4, x equal to 3, f x is 9, x equal to 4, f x is 16, and we want to know if x is 5, what is f x. So, this is an example of a training set that we are given, and we want to learn the function f. In this case, one good guess is that the function f is a square function, that is f x is x square. I mean, this is not really a discrete learning problem, but this is an example of learning a function. Another example, suppose you want to learn the concept of an apple, whether an object is an apple or not. You are given some training examples. For the training examples, these are the features that you are given. For every object that you are given, you know the color, shape, the diameter, whether it has a stem, and then it is labeled whether the object is an apple or not an apple. And you have got 4 examples. The first example, the color is red, shape is round, it has a diameter of 4 inch, it has a stem and you know it is an apple. The second example, color is yellow, shape is round, diameter is 4.3 inch, it does not have a stem, it is an apple. Third example, color is green, shape is square, diameter is 5 inch, no stem, not an apple. Negative example of an apple. Fourth example, color is green, shape is round, diameter is 3 inch, it has a stem and it is an apple. Now, you could learn a rule or a set of rules to distinguish positive examples of apple from negative examples. These rules are called classification rules. For example, rules could be round means apple, or stem implies apple, or diameter less than 5 inch means apple, or round and diameter less than 5 inch means apple. So, these are some of possible rules that you can hypothesize about an apple. Now, you see in this case we are looking at rules expressed in a particular type of language. These rules are given in terms of the features, but these features are expressed in some language. For example, round and diameter is less than 5 inch. So, here we are expressing the rule, the antecedent, as a conjunction of constraints on features. Similarly, we could express a rule as a disjunction. We could say round or diameter less than 5 inch implies apple. So, this is an example of a disjunctive rule, or we could express it in other forms. So, we could decide a language in which to express the rules, and this defines the set of hypotheses that we are considering. Now, what type of hypothesis should we consider? Suppose F is a set of rules, then the space of hypothesis is all rule sets. The space of hypothesis could be simple polynomials. The space of hypothesis could be decision trees. The space of hypothesis that we are considering could be neural networks. Some of these we will discuss later in this class. So, we have a choice about what type of hypothesis we are going to consider. We are trying to learn a function f which we do not know, and we are trying to find an approximation to f. We are trying to make a hypothesis. This hypothesis, we will have to choose this hypothesis from a set of hypotheses that we will consider. This is called our hypothesis space. And what set of hypotheses we should consider? That is what we must decide. So, we will express by capital H the space of all possible hypotheses that a learning program considered. Then our objective would be to find one hypothesis which is a member of this hypothesis space. We want to find that hypothesis which is the best. We want to find the best hypothesis of this hypothesis space. What is the best hypothesis? It is that which fits the given data the best. Okay. So, this is a process of search. So, in order to find this best hypothesis, we will search through this hypothesis space to find that hypothesis which fits the data in the best possible manner. So, this is an example of a hypothesis space. In this hypothesis space, there are a large number of hypotheses. For example, H1, H2, H3, H4, H5, these are some of the hypotheses in this hypothesis space, and we want to select the best of these, the best hypothesis in this hypothesis space. Now, suppose you want to learn the concept apple, and this is an example of a hypothesis space, and you have a hypothesis here like round and diameter less than 5 degree, red and round and has stem, not a square, round. So, these are some hypotheses which are there in the hypothesis space, and we want to select the best of these hypotheses. Now, let us go on to some more definitions. So, the training set is the set of all training examples that are given to the learner. They are called the training set. So, training set is the set of all examples that are given to the learner, and the testing set is the set of examples on which the learner tests his hypothesis. You see, on the basis of the training set, the learner will learn a hypothesis, and the learner will try to evaluate how good the hypothesis is by looking at another set of examples, which is called the test set. Now, a consistent hypothesis. So, learner on looking at the training set will find a hypothesis. The hypothesis that the learner has found will be said to be consistent if it is consistent with all the training examples. That is, the hypothesis must predict the correct label of all the training examples. Such a hypothesis is called consistent. We cannot guarantee that a consistent hypothesis will necessarily always give the correct labeling for each test example, because we have not seen the test example, but we can check whether the hypothesis correctly labels the training example. A testing set is the set of all examples that are given to the learner after it has learned the hypothesis, on which its accuracy will be tested. Now, suppose the examples are labeled plus and minus, then the consistent hypothesis is a hypothesis that implies that labels as positive all the plus examples and none of the minus examples. So, that is a consistent hypothesis. Now, let us look at this diagram. Suppose this one is the instance space which consists of all possible examples, and suppose this is the true function f that our system is trying to learn. This is f. Now, a hypothesis, so this f labels the instances inside this circle as positive and the instances outside this circle as negative. Now, this other circle is the hypothesis h that your learner finds. Now, you see, in this region the h and f agree in the labeling of these instances. H makes mistakes in this region, this blue region, and in this black region. So, these are the two regions in which H makes a mistake. Out of this, an example is called to be a false negative if the hypothesis says it should be negative, but it is actually positive. Look at this blue region. Your hypothesis states that these examples must be negative, but these examples are actually positive according to f. So, these are falsely negative by your hypothesis. So, this is a zone of error of your hypothesis. Look at this green region. Your hypothesis says that these instances should be positive, but they are actually negative according to f. So, this is another error zone. This is said to be the false positive for your hypothesis. So, an example is a false negative for a hypothesis if the hypothesis says it would be negative, but it is actually positive. An example is a false positive for a hypothesis if the hypothesis says it should be positive, but it is negative. Okay. This big thing is the instance space. All the instances are here, and this is a particular concept. Inside the circle we have positive examples, outside the circle we have negative examples. This other circle is your hypothesis. So, one more definition, inductive bias. You see, when you are making an inductive inference on the basis of looking at some examples, you are making a hypothesis. That hypothesis may not be fully correct. You see, so you are making a jump, you are making a conceptual jump, you are assuming something extra, right. So, when you see some data, you could infer different possible hypotheses. Now, which one of them would you select, right? You could find out, you could try to find out that hypothesis which is consistent, but suppose you find several hypotheses which are consistent with your training set. Like in the apple example we saw, we could find several hypotheses which are consistent with the 4 examples. Which one of them would you select? In order to select one of them, we use the concept of inductive bias. So, inductive bias is a bias or a preference for one hypothesis over another. Okay. And there are different types of inductive bias which are used by different learners. For example, simplicity could be a bias, or most general hypothesis could be a bias, or choose the most specific hypothesis, that could be a bias. So, among hypotheses which are both consistent, we choose one of them according to some bias that we have. For example, suppose you want to learn the concept apple. Then you could learn a set of rules to distinguish positive from negative examples. These are called classification rules. So, these are rules that we have already seen, and then you could say, in order to select among the rules, you apply a bias. This is called inductive bias. Now, how do you choose the best hypothesis? Now, one way in which you could choose the best hypothesis is you find that hypothesis which, you see, among 2 hypotheses which are equally consistent on the training examples, you should choose a hypothesis that is likely to agree with new examples. So, our real goal in machine learning is to find a hypothesis f dash in H such that it will correctly classify new examples. So, ideal thing would be to choose that f dash so that probability that f dash x does not agree with f x is smallest. Okay, we want to choose that f dash so that it agrees with f most of the time, but we cannot compute this probability because we do not beforehand know all the instances, all the labels of instances. And how we will evaluate the performance of a learner? We will evaluate the performance of the learner by seeing how well the learned hypothesis can predict the classification of unseen examples, examples that we have not yet seen. So, in order to be able to get an idea, you see, if we use the training set for classification, we will not really understand whether our hypothesis is performing well on unknown examples. So, we should apply the hypothesis that we have learned from the training set on new data. So, test set should be disjoint with the training set. So, in a concept learning, our problem is to learn the target concept f from a set of training examples, and to evaluate, we measure the predictive performance of the learned hypothesis on a set of test examples called the test set, and we require that the training and test set are different from each other, so that there is no bias. Okay. So, these details we will look at in the next class. So, let us come to a few questions for this lecture. Question number 1, consider the problem of trying to recognize handwritten digits. You have to formulate this as a concept learning problem. Specifically, you have 3 tasks. A, clearly specify what are the possible features. B, how do you get the training set and the test set? C, how will you measure the performance of your learning algorithm? Second question, consider the problem of trying to play a game of Ludo. Formulate this as a learning problem. Clearly specify what your system will try to learn. B, how can you get the training examples for this system? With this, I stop today's lecture. In the next class, we will look further at certain definitions of concept learning problem, and then we will move on to some algorithms and frameworks for learning. Thank you.